Good afternoon, everyone. Welcome to another live star stream of the UTA Planetarium. My name is Levent Gürdemir, and in the studio, program coordinator and together, we are, by the way, in our new. May not notice background change, but picture. But we are in our substitute, and today we are going to talk about something interesting.
Very interesting. I do want to say, if you guys see Levent looking off in a different direction, we've made some changes, so please be patient with us.
Yes, because the camera and the monitor is find me just at different camera. But well, today is June and day for astronomy. That was the summer solstice. That's the day that summer astronomically starts. That is daytime. We get the daylight longer than any days are. Late and light saving effect.
You know, Levent, I do have to say that I know that we do this every time. June 21st happens. It's summer, and it's the longest day of the year. And then after that, all the days they get shorter, right? Specifically, but here in Texas, the days feel like they get longer. Am I wrong? That's how it feels, and it's maybe just because the heat is so oppressive. I don't know.
Well, if you look at the sunset is now around 9 o'clock, right? And at the sunset times every day, it's going to get earlier and earlier until at the end of December. And at one point, the day and the night lengths are going to be equal. We call those times equal. There are two in the one is March and one is in September. The days are days are very long right now, but every day they will get shorter and shorter until winter solstice.
Yeah. All right, so we're gonna go ahead and bring up our subject for today.
There's a comment about my audio.
Yeah, I
Cutting
saw
in
it.
and out. Is that still the case?
I think we've recovered by now, but we'll keep monitoring the problem for sure.
Okay, I will blame the extraterrestrial.
Definitely.
How about that?
We got to talk about UFOs, Levent. It's time to talk about UFOs.
Well, yes.
Extraterrestrials.
Tell me, what is UFO?
Well, that's the problem, I think, because in pop culture and on TV, on social media, because that's what rules everything now, UFOs are aliens, and by aliens I mean extraterrestrials. But in reality, I think you and I and other people who are like-minded, UFO means we don't know, right? It could be a plane we didn't know about. It could be anything, right? So, what would you call a UFO?
Well, anything that we cannot identify whether it's an airplane. Like, if, for example, if you don't know what is an airplane is a UFO. If there is a light in the sky and you don't know what it can be a space station, National Space Station, it can be a satellite, it can be maybe a shooting star or meteor event. If you don't know what it is, then it's certainly UFO. But UFOs are in general linked to the extraterrestrial visitors that who supposedly live in a different planet, different star, different galaxy perhaps, and that they travel in a saucer looking vessels, and they hover in the sky. They do maneuvers, and they, I don't know, take pictures or video perhaps, and even sometimes try to communicate with us. Those are blamed as UFOs, right?
Yep, yeah, they definitely
in most
are.
cases. Okay, here is the fact. I think we got a lot of questions. couple weeks ago when you opened the can of worms, Jim, and talked about a nice newly published article regarding warp drive.
Yeah. So when people bring up UFOs, the question that is so important that's just missed all the time is if it is an extraterrestrial, it's an actual extraterrestrial. How does it get here? Right, space is huge. When people in the planetarium ask me that question, what and you get it all the time. I'm sure you've got it plenty of times too. What do you think is most fascinating about the universe? And for me, it's the size. It's enormous. And if you're going to travel from another star system to here, as far as I know, I don't think it's possible. I'm curious about the audience, so I'm going to drop a poll. I want you to respond to the poll if you can. We'll discuss it at the end of the show, but please do so. Yeah, Levent, do you have any comment about how do they move that far?
Yeah, let's talk about the facts. The only place we were able to travel with humans being on board was to the moon. So beyond that, we sent rovers and even drone to Mars. We sent robots to Venus, and we certainly, explored the rest of the solar system with satellites. Even for satellites, unmanned missions, it takes months to go there, if not years. The moon is the closest celestial object, the closest neighbor of Earth, and it took with the 1960s technology, it took about 40 days to go there. It takes a little bit shorter, but the traveling to another star is not something like that. We cannot just go in days, even years. So for that reason, we always imagine the fastest possible traveling ship. And that ship must be traveling at the speed of light because this is the fastest thing we know in the entire universe. How fast is speed? The light? It is 186,000 miles per second. Well, we are not familiar with miles per second unit because we usually, when we are driving, we are using mile per hour. If we convert that, do the conversion, that is reading 670 million in your dashboard. Then your car is
That's
traveling
big.
at the speed of light.
Big number.
So let's take a look at what we can achieve with the speed of light. If we are traveling from Dallas to China, Beijing, for example, it only takes 0.04 seconds. Only a small fraction of second can take you to Beijing immediately almost. But if you take a flight with American, it takes 14 hours.
Oh,
So
man.
if you are going to the moon at the speed of light, it takes 1.3 seconds. If you are going to the sun, it takes about 7 minutes. And with that speed, the closest star to the sun takes 4.5 years. Imagine 4.5 years.
Yeah.
So if you are looking to cross the entire galaxy, it takes 100 million years.
Wait, million years?
100 million years. And if we imagine like we are short-lived species, and if we are traveling at the speed of light, if we put a newborn in the vessel and send it to the space at the light of speed, then newborn in the entire life can only visit 4 to 5 stars. Ooh. And those are just the closest stars, and the remaining stars will be out of the lifetime of humans.
This poses a big problem, and it brings exactly the point of the show today, right?
So yeah, I mean that brings the necessity for speeds greater than speed of light, because apparently our lifetime is not enough to just even travel our galaxy is just so big for our life. Okay.
Right.
I mean the faster than speed of light is a different issue, but I think that the main issue is you have let's say a vessel, and then you are going to drive it at the speed of light. First, you need to accelerate, right? You need to accelerate your vessel to the speed of light. And how long it is going to take to see the speed of light, 186,000 miles per hour or per second in your dashboard. So that's the problem, because to To do this, we have limitations, and that limitation is the g-force. The acceleration or deceleration come with g-force. For example, if you are just in your car and accelerating, you are experiencing a slight g-force. If you are in a roller coaster, you are experiencing more g-force. If you are free falling, you are experiencing 1g acceleration force. Human body can stand 9g only for a few seconds. That's why most commercial aircraft, the seats are designed to take 9g forces. And I was wondering where that 9g comes from, because if the deceleration or acceleration of aircraft exceeds 9g's, that means everybody on board is dead.
That's not funny. Sorry, I shouldn't laugh.
9g's is that way. 5g's we can only stand for 2 minutes, and the 3g's for an hour. Okay, after 3g's, after 1 hour, then we have significant damage in our body. So how long would it take? Let's say if we are taking 3g's, it would take 2.5 months to go to the half of speed of light. Not even speed of light. Half of speed of light takes 2.5 months. Even if we use 9g's, we would be dead anyway, but it would take 19 days to go to that half speed of the light. So it takes apparently forever for us to accelerate to light speed. And also there is another problem, and that is the Einstein. So Einstein says, if a mass, an object, is accelerating to the speed of light, its mass increases and the length shortens. So at the speed of light, mass becomes infinite and the length becomes 0. So that means we will be indefinitely massive, but at zero length, like a dot, objects. And moreover that, but there's also interesting fact, and that is in the special relativity, and that is the time dilation. And according to the Einstein's relativity theory, it is possible for somebody to, with the 1g acceleration, we can travel the entire known universe, because there's very interesting things about time when we accelerate.
Definitely. I think now's as good a time as any, Levent. Since we brought an extremely special guest, we're so grateful to have him. And I'll go ahead and let you introduce him. We have somebody here to help talk to us about all of this.
Absolutely.
So I'll move out of the way, and you can go to introduce us.
Let's welcome Dr. Ben Jones of UTA Physics Department, because we will be talking about very interesting topics with the special relativity, general relativity, and the speed of light. So that is a little bit beyond me, and we thought that Dr. Ben Jones, who is in the actual faculty office right now, and you can see the cool blackboard, he's apparently working on some cool things.
Wait, this looks like a set. He's setting this up. What did he do?
Welcome, Dr. Ben Jones.
Is it real, Dr. Jones?
I promise you that this is real science happening in my real office. This is a problem I was going through with my graduate student who's working on new ways of detecting rare radioactive decays in time projection chambers. So it's real. Hi, everybody. Thank you very much for having me. So let me give you a warning, first of all. Like, one of my favorite things to do in the whole world is like talk about physics, and I'll probably talk in much more length and detail than anyone wants. So Levent will have to interrupt me and guide the conversation. So I'm an astroparticle physicist here at UTA. That means I'm not the guy who like uses the telescope to count how many stars and stuff there are in the universe. That would be an astronomer. But I'm the guy who tries to understand how the fundamental laws of physics led to the universe looking like it looks. These kinds of questions of what sort of travel, subluminal or superluminal, is possible are the kinds of things that I like to think about. And so I'm happy to answer questions and discuss those things. Levin, I wanted to make one comment on your points. I completely agree with all of those things that you described as being the challenges, especially the acceleration challenge and the amount of energy it would take to get you to the speed of light. But I did want to comment that this issue of relativistic time dilation actually helps you in a sense if you're trying to explore the universe at high speeds, because this idea that a newborn baby could only visit 4 stars is true according to the flow of time as perceived on the star. But the baby on the spaceship actually would live millions of times longer than a normal human lifetime, according to people who are stationary on those stars. And so if you really got very close to the speed of light, you could explore as much of the universe as you ever dreamed of. And one way of thinking about this is that light rays are the only things we know that go at the speed of light, exactly at it. Some things go close to it, and I work in my research with particles at like 99.999999% the speed of light. But the only things we know that go actually at the speed of light are light rays. And technically, for a light ray, it's going so fast that time does not pass for it. So a light ray, if it experienced things, it would be experiencing every place it goes in its lifetime simultaneously. And so, if you imagine getting yourself very close to that speed, then you could actually go kind of arbitrarily far in your lifetime. I mean, of course, civilizations would like be built and die in a microsecond to you on those stars. So it's questionable how useful that travel would be. But in principle, you could explore quite large cosmic horizons, I think.
So in this case, we may be able to travel at a maybe different galaxy, but when we turn back to Earth, so people may not be there anymore.
Right. Certainly, if you went at the speed of light to something billion light years away and came back, there would certainly be no civilization left on planet Earth. It would be just smoking rubble. By that point, I'm sure.
That sounds terrifying. Hard pass on that. Hard pass.
So what is that new article came about maybe making the possibility of traveling at the greater speeds than speed of light?
The Alcubierre drive.
Yes, the warp drive geometry. So to talk about warp drives, I think we have to start off by talking a little bit about the general theory of relativity. So the general theory of relativity is a theory of gravitation, which Einstein came up with. And it basically says that gravity is a force which is not really like the other forces, like electromagnetism or the other forces we know about, because gravity acts in a way whereby the force is transmitted by distortions in the nature of space and time. So when two things are attracting each other gravitationally, they're not really sort of like pulling each other with a force in the traditional sense. They're changing the nature of space and time such that the natural motion of these two objects as they go forward in time is to come closer together. Now, that might seem like a slightly technical distinction, but what I really mean to say is that the way that gravitation acts is something which really changes the definition of those things that we understand space and time. And I don't know if any of you have seen the movie Interstellar, but there's a really nice illustration of general relativity in that movie where when people are on these like very massive, near a very massive object like a black hole, time runs at a different speed for them relative to how it runs for people who are far away from that object. And so really we call it curving space-time, but really it's just distorting the nature of space and time. So basically we accept the principle then, and this has been tested, by the way. It's experimentally verified by looking at the way that light bends around stars and things like that this general theory of relativity is true. So we accept the principle then that the general theory of relativity means that gravitation involves changing the nature of space and time. So that means that you can consider universes or consider situations where you put very massive objects in different places to like bend the space-time in a way that's kind of convenient for you. Oh, there's a nice animation here of general relativity in the bottom, I see. So that's what it looks like when like the moon is orbiting the Earth, right? It's like moving around in this bent like space-time. Now you can imagine if you could control where you put all those planets, you can make any shape on this this thing that you want, on this manifold that you want. And so you could make your like great pinball machine, right, and send things in any trajectory. Now, the idea behind these warp drives is you can imagine ways of distorting that structure of space and time such that there's a small piece of it that moves along, which is locally just like flat. It's locally like there's nothing gravitating inside it, but it sort of moves along through the fabric of space-time at a speed which other observers would perceive as faster than the speed of light. Now, that's very strange. And this is actually a long debated and controversial topic. Could you ever realize such a thing? Because the equations of general relativity, which govern the ways you're allowed to bend space-time, there is a way of writing down a solution to them that looks like that, that says, okay, you bend it this way and that way and the other way, and then, you know, this thing will go apparently faster than the speed of light. The question that's been bugging people for a long time about warp drives, though, is could you ever do that with an actual physical arrangement of things? Because the way that people usually try and make that is they say, okay, we have a positive mass here, and then we put a negative mass over there. And if you're a physicist, then alarm bells ring. You're like, what's a negative mass? I don't know anything that has a negative mass, right? So like for a long time, people were like, okay, you could do it if you had these arrangements of positive and negative masses, and maybe this bit over here, you just say that bit's infinite. And, you know, then you start to ask questions, could you ever do that actually in the universe? This new paper is quite interesting because it seems to come up with a configuration of the space-time that has this like warping piece in it, which doesn't involve any negative energies or negative masses. So it seems to be able to be put together by arranging in a very careful way only objects that look like they could physically exist in the universe. Now, could you actually do it with technology? Now, that's a different question, because when you're trying to put enough mass somewhere to really distort the structure of space and time, you're talking about gigantic masses. Like the sorts of masses that distort in an appreciable way how fast time flows are things like black holes or, you know, neutron stars, like very, very dense, extremely heavy objects. And, you know, you can't really like pick those up and move them around to your taste. So this paper is actually an interesting theoretical advance because it shows, I think, that in principle, or at least it claims to show, I maybe haven't digested all the details enough to make a claim about whether it's completely valid, but it seems to show that there is a way of arranging physical objects that would allow this like warp drive like travel, basically. I want to say one more thing about this, which is that the caveat I would give about, you know, it's somehow it's easy to find all the technological reasons why something's impossible, right? You need all this energy, you need all this blah, blah, blah. But you always have to account for the fact that at the moment, we still don't understand everything about the way gravitation works. We understand how gravitation works around big astronomical objects. We understand roughly how gravitation works in galaxies, although to explain our observations of galaxies, we have to introduce this mysterious dark matter substance to explain why gravity is doing what it's doing. So one could argue maybe we don't understand gravity super well, even in our local galaxy. But one place we especially don't understand how gravity works is on very small scales. When quantum mechanics and gravity become both important. And
do you think
I
the
imagine
gravity pulls or space pushes? What do you think?
Sorry?
Was the gravity pulls or space pushes? What do you think?
I mean, both, I guess. I mean, they seem to both be reasonable descriptions of like the observational phenomena, right? But anyway, I just wanted to end on this comment that any kind of warp drive device we make, you know, we might make, is going to be some device we build in a laboratory, and it's probably going to do something on the very, very small quantum mechanical level to manipulate space-time. And we don't necessarily understand the way that gravity works on those scales yet, which is why it's super important to continue pursuing these lines of experiment that we're working on in particle physics to understand the interplay between gravitation and the other forces, because these are the sorts of technologies that kind of research could enable in principle.
And usually it is commonly asked that can we use black holes to travel to a different part of the universe through wormholes and white holes?
So wormholes are another example of one of these solutions to the equations of relativity that you can write down. And on paper, it's like, okay, yeah, that looks like something that could exist, right? That solves the equations. It's okay. Einstein and Rosen wrote that down at first, I think. We've never seen one, though, in the universe. And even though it could in principle exist, it's not clear how it would be made. And so but the thing is, there are very plausible ways that they could have been made, especially in the very, very early universe. When again, it all comes down to quantum gravity, really. In the era of the very early universe, when the temperature was very high and quantum effects and gravity were both important, there could have been primordial wormholes created. There's also interesting research going on right now relating to something called the black hole information paradox, which is a question about how information does or doesn't leave black holes when they radiate, because they have a finite temperature. And people think at the moment that there's some idea that at the surface of the black hole you can generate tiny wormholes which connect the inside and the outside of the black hole together. So there are plausible ways to imagine natural wormholes being generated. We don't know a way to generate one by hand, but that doesn't mean there isn't a way. It means we haven't found it yet.
Well, thank you very much, Dr. Jones,
Yep.
for all of your feedback and explanations. Hope to see you in the future again with another live stream here.
Before we let you go, Dr. Jones, I do have to ask: are there any questions that we're not asking that you think are important? The general public, not necessarily us, about
Yes.
Interstellar travel and
Yes.
problems or
Yes.
the lack thereof.
Great. These are great questions. So I did have I could talk for hours and hours, so I'll try and be fairly brief. But when Levin was explaining all these limitations, I completely agreed with them in terms of physics principles. But if we're addressing the question of whether like UFOs, or there's a new acronym for UFOs, right, which I can't remember what it is, UAPs or something.
UAPs, yeah, unidentified aerial phenomena.
If we're trying to really assess the question, are those aliens? We would need to ask the question, like, not could we travel to another star system, but could they have traveled to us, right? And one thing that we should remember, I think, is that the nature of the passage of time is something which is really kind of connected to our consciousness. I mean, we perceive time going at a certain speed because of the way that we're biologically wired, and we live for 100 years if we're lucky. But some other civilization, I mean, there's no reason that they would even have a finite lifetime, right? They might have been alive a billion years per being, so they wouldn't in principle have to travel here.
That makes me extremely uncomfortable.
I think that's gonna be the you are pointing a flaw in the Drake equation, I guess.
I guess so,
because
right?
there's a lifetime
Lifetimes.
factor in that Drake equation, right? So
Yeah.
what if we don't have that factor of lifetime? What if there's an infinite life?
Yeah. I mean, and it wouldn't necessarily have to be a biological system that could exist alive forever, right? Because I mean, that does seem hard to imagine. But you could imagine that, like, if you travel, this has been done in sci-fi, right? You get cryogenically frozen, and then that means your effective lifetime is much longer, even though your conscious lifetime is the same length. And so, in principle, then that unbinds you from these limitations of the great distances of travel, right? You could get there. So,
that feels so. I can't describe why that makes me feel uncomfortable, but it hurts.
Well, yeah, that's a great way of, I think, doing science, because when we question the things, then we can come up with, like, sometimes, like I was trying to point out that my purpose was not to discourage for space travel, but if we just look at the from the technical point of view, with just considering ourselves on the planet Earth, the time is as we perceived, and the mass is as we perceived, and with the limitations of our body, etc. And even from engineering point of view, it looks like impossible to achieve or go to the speed of lights. However, if we just involve this great physics, great general relativity into the account, then we are just opening a lot of possibilities, and that, I think that's why I like physics.
Physics is a beautiful thing, and I mean, that's the point, right? Is in physics we're asking the questions like, what is possible in principle, right, rather than what is possible for us right now. And many of the things that are possible in principle eventually become possible for us as we develop our technology. So
yeah. Absolutely.
Well, thank you so much, Dr. Jones. You are fantastic, and we'll definitely squeeze you on sometime in the future, as long as we can take time away from your day, which I'm sure is precious.
Thank you
very much. All right, I think we are back. Let's see if there are any questions from our guests.
We got a bunch. A whole bunch of questions. So I want to run up to Kurt. He had a question early on that needs to be brought up, and that's what cryogenic transport shuttles are for. Wake me up when we get to the next habitable planet. I think this is a really interesting question that Kurt brought up, mostly because of what Dr. Jones said, and the time frames in relativity can make things confusing, right? Because 4 years on Earth time, if you're traveling at the speed of light, is how long it would take you to get there. But if you're moving at the speed of light or near the speed of light, time's going to work much different for you, like you mentioned. So if you cryogenically freeze yourself, it wouldn't have to be for very long to travel to all these stars. I don't know. Do you have any comments on that point, Levent?
Well, I think the most interesting point over here is with all the technical impossibilities. But if you think about just traveling at the or near the speed of light, and factoring the time dilation, it's amazing. It says the article says, in one lifetime, one person can just travel the entire known universe. It's amazing. But again, I mean, the time is way different when we go to much higher speeds.
Definitely. So hello to Janet and Johnny. We had another point that Kurt made that I mean, we still have Dr. Jones here, so I guess we can kind of get him to clarify, because maybe we presented it a little confusing somehow. I'm not sure. But Kurt Copeland asks, so I can post that up there. Going the speed of light is like growing old?
Going the speed of light is like growing young, as a matter of fact.
Okay, there we go.
Yeah, if you take, there's a thing called the Einstein twins paradox, which is a very famous example from special relativity. And this is a thought experiment. Obviously, no one's ever done this, but it's a thought experiment that illustrates how it works. So you imagine you start with two twins on the Earth, and then one of them gets in a spaceship and goes close to the speed of light to a distant planet and comes back, and they meet again. When they meet again, they'll be different ages, because the one who goes out, accelerates, and comes back experiences time passing at a different speed than the one who's on the Earth. And the way, it's actually a famous, if you study physics at university, I teach this in modern physics to second year physics students. If you study physics at university, this is like a pretty hard problem you have to work through in special relativity to figure out which one gets older faster. But the rule to remember is, if you keep moving, you stay young. That's how you remember which one.
Wait, we tested this. This is a real thing. We had two twins. One went to space and one stayed on Earth. This is real, right? The Kelly brothers. Yeah. Scott Kelly. Yeah, this happened. This is an interesting point, but yeah, thank you for bringing that up.
And also from the health perspective, it's also true, right? If we just keep moving, we stay young.
Exercise.
That's right.
Yeah.
Well,
actually, that brings another whole other problem event, because how do they know that it's exercise keeping you young and not moving? You're just aging a little bit slower, infinitesimally slower. But
with the real twins, I'm sure that the one who went to space and came back in kind of worse physical shape than the one who stayed on it. So I'm not sure that was a great example, but we have also done the experiment with atomic clocks, where we sent one to space and left one on the Earth. And if you compare the time on the atomic clocks, then you get a much more reliable measure of this effect. Not quite as exciting as twins, but more reliable.
Awesome. It looks like Kurt is clarifying himself and saying that Levent, when you were talking about approaching the speed of light, it made one infinitely massive and compressed. So he was joking about growing old. I don't know. Anyway. Interesting point. And this is a little off topic, but Johnny Alejandro commented, how helpful will James Webb Space Telescope be to study planet formation? I don't know, Levent. Either of you want to comment on that?
I don't know the instruments on the latest instruments on James Webb Space Telescope.
Do you have any comment, Dr. Jones?
Yeah, first of all, let me give the caveat. This isn't my field. That would be the observational astronomy, right? The people who really go count planets. I mean, my understanding is that the James Webb Space Telescope extends the like from the Hubble extends the range of wavelengths being probed further
Yes.
into the infrared, and so that means you can see further back in time because light. Well, I should clarify what that means. So, like, whenever you see an object in the universe, like shining at you, a star shining at you, you're seeing the light that arrives at you, which left that object a long time ago. Because if it's a billion light years away, it took a billion years for the light to get to you, right? So the objects that I study neutrinos from black holes devouring galaxies. Oh, have I lost the connection? Am I still here?
No, you're still here. You're still here.
I'm still here. Yeah, I study like neutrinos emitted from black holes devouring galaxies, and the neutrinos I catch in my detector were made 50 billion years ago by that black hole. So, but what happens in that time as the light is traveling is the universe is expanding, and that causes the wavelength of the light to stretch. So, you know, blue light has short wavelengths, red light has long wavelengths. So something that was blue would become red as it traveled. It's called redshift. And so the further away you look, you're looking both further back in time because the light left earlier, and you need to look at redder light. And so the James Webb Space Telescope, I think one of the things it's doing is letting you look at redder things which are further away and further back in time. But again, that's the caveat. That's not really my area. So that's my understanding.
Yeah.
Well,
Thank you very much, Dr.
Yeah.
Ben Jones, and hope to see you in a different live stream with another topic. Great topic.
Yeah, maybe in person next time. We're coming over the hump of this COVID thing, so hopefully.
Great. Then I can even wave my arms and be enthusiastic.
You don't have arms. Okay.
All right. Is there anything else, Jim, that we haven't covered?
I'm sure there's plenty we haven't covered, Levent. We have more to talk about. Like he like Dr. Jones mentioned in the episode, when we talk about life from other places, life from somewhere else in the galaxy, another star with another energy output or what have you, how does that help the life grow differently from us, and how we'll be able to interpret them, right? A lot of really strange, peculiar things that pop in there.
Well, yes, we are just scratching the surface on the potential life on a planet, because there are a lot of factors. And again, we are always thinking like life like ourselves, right?
Yeah.
We are just looking for the conditions, the temperatures like Earth-like, and the atmospheric conditions Earth-like, and the pressure conditions Earth-like. We are talking about liquid water, but we know that even on our planet, there are a lot of species that they live without the existence of light and even the oxygen. So, I mean, these are just the possibilities, and it is likely that some different form of life, and I always make the point that when we talk about life, we are not just talking about like humans like us, you know, talking, thinking. Even a mold is a life form. So if we can find, like, for example, mold on the surface of Mars, that will be a discovery. That will
Huge. It would be enormous.
Like finding life on the planet Mars. And we will look for the other type of species, like, you know, maybe humans, like animals, or something else that we never seen or think about before.
It's easy to box ourselves in with the expectations of a bipedal creature with eyes and a nose.
Main thing we are looking for is, you know, there are types of stars, and some stars radiate more ultraviolet radiation and blue light. So one thing we know, that all the species or life is depending on DNA on Earth, and the UV light, ultraviolet light, is damaging the UV. So if we are thinking, if the star should have some you know, limit to the density of the UV light it is emitting, or the sun is actually the providing us a lot of UV, which can be just dangerous for us, but we have that atmosphere around Earth, our planet, and it is absorbing significant amount of UV light, so our DNA is not getting damaged.
Yeah, definitely. All right, Levent. So to recap the episode, I want to ask you the question outright.
Yeah.
What do you think the chances are of there being a warp drive Actual warp drive technology in the next 50 years. Specifically 50 years.
Well, my opinion on that is no, but who knows? There are great scientists working on.
Well, I was really hoping you would say yes. I don't know why. I just wanted an argument because I have to say no.
Well,
I don't think
I'm
so.
saying
Maybe,
no.
but
It's not because that we will not be able to figure it out. But usually, if you look at the history of science,
mhm.
um, discoveries come into implementation of the technology. It takes a long time.
Yeah.
We discover something like we knew these even like nuclear energy, for example. It has been studied for a long time, and then it came to the life much after. So
That's that you just made a really good point, Levent. Nuclear energy was one thing that people talked about, theorized, and then as soon as somebody said, "Hey, look, this is possible," because it was a hey, this could help us in war, it was really quickly studied, and they put effort into it big time. So we have to. No, I don't want to bring that up. We don't need to start a war to get people to further their research here.
yeah, that's a whole different.
Kurt bring up something that I remember seeing this too, Kurt. He said, I seem to remember an article about evidence of methanogens being found on some planet or moon in our solar system. No, so there's talk of there being a type of air on Venus that we think might be able to host life, but it would be in the upper atmosphere, so it would be something
In the clouds.
Yeah, this would be something that would be really strange to imagine as an Earthling, something that could stay in the air, indefinitely. And then there's also some research like where they thought they found something in a lake in California or something like this. Maybe this was like 15 years ago. I remember seeing this come out, and I think that was mostly just proven that there was a different, not oxygen-based life form out there. So
Yeah, we still need to do an
carbon.
episode
Sorry.
on Enceladus.
Yes.
Because Enceladus is after Mars. It is going to be the focus point for scientists to look for the signs of life.
So many places: Titan, Enceladus, Europa.
Yeah.
We definitely have to have a whole episode on this for sure. I don't think there's going to be a warp drive. You don't think there's going to be warp drive, and I have to say that during our poll, most everyone else didn't know what to say. It was pretty even all the way around. Some people said yes, some people said no, and then we had people saying yes, but after 50 years. Yeah, I think it's possible after 50 years, but humans have to survive that long. That's my problem. We have to somehow live for the next 100 years. And in a state that we can still create technology effectively. So see how that goes. But not in my lifetime. Anyway, do we have anything else to bring up?
Well, things change. When we look at the pictures of like an American family, the picture was taken 100 years ago, and we just look around the picture to see the technology, right? And we don't see much. And now we have all smartphones, internet. We are doing live stream from our studio to the entire world.
Yeah.
I mean, the things changed. How much things changed in 100 years, and how much things will change in the same direction in the next 100 years.
Good point. We'll see. Maybe we'll all be surprised. I personally prefer to be surprised.
Imagine somebody 100 years later will be maybe watching our live stream, finding in the archive or something, and they will be saying like, "Oh, poor guys." Just had just the camera and just the streaming technology nowadays.
Yeah.
They didn't have much.
In my experience, I mean, the concept of warp drive's been around for a long time, and it still hasn't happened. I mean, Star Trek. I doubt they were the ones who pioneered this concept, but Star Trek has been going to warp speed since 1966. So it's
one misconception. There's a big misconception in Star Trek, and that is the star trails.
Star trails.
You are traveling at the speed of light. There is no reason
yeah.
for stars to show trails.
There's a lot of wacky things. I love this. Let's bring this here. this concept of the star trails. This is what you're talking about, right?
Yes.
Okay, yeah, that's just making sure we're on the same page. Yeah.
All right.
Okay.
Let's
End it for
say
today.
we are going to be here next week, and if you have any questions, even during the week, you can just let us know, post on our social media, and we'll discuss that in the next live stream next Wednesday, same time, 1 p.m.
Okay. Thank you guys so much. See you next week.
See you next week.